で、頑張って英語で打ってね、you black is no とか。
Okay, so I will record the session as a backup. Okay, so we will discuss few of the question today. Question 1, 2, 3, and 4 and 6. So question 1, 2, 3, 4, and 6. 1, 2, 3, and then the 4, I think I put here. 1, 2, 3, 4. Okay, and then we have 6. So you can see the questions actually additional, something additional from whatever we have in the lecture slides. So you remember we have the homework. So after each session, the lecture or tutorials, I will share the written notes, like the one I'm solving over here during the lecture or during the tutorial. So I will share to the Telegram. I won't post to the My Times, but I will share to the Telegram. So anything you miss, then you can refer back to the one I handwrite. So from there you can do your revision together. So I will share this one as well. So if let's say you cannot finish copying during that time, you just put a note there because the whole copy later will be shared to you to the Telegram. So you need to check the Telegram on daily basis lah. So most of the time I will share right after the class, or maybe I have other classes ongoing, then I will share on the same day. Okay, so this is the revision. I ask you all to print out this Laplace table. So these Laplace tables you are going to refer for the first 6 weeks, and then we still have the Laplace for the rest of the weeks, because the first 6 weeks you learn how to model a process. So after you already know how to model the process, to represent a process using an equation, either you solve using 3 methods. So we already cover one method during your lecture. We already covered integration method. So some quick recap. So integration method, we have few examples already, and I actually give you few homework from lecture 1, so that you already you can master how to solve the question using the integration method. So now in the tutorial, we actually solve using 2 methods. One is, I don't think I put the integration method, but I include the introduction of like a recap of the Laplace transform. Just like question 1, you have learned this in your Maths 2 last maybe 2 or 3 semesters ago. So we will do some recap about the Laplace transform. Can you solve all these, the simple one? Okay, and then the question 2 will be something like, can you solve the differential equation, like Laplace of the differential equation from 0 order, first order, second order until n order. So we have the term 24 and 25. So in your Maths 2 last time, you are not using the same table. So this is a different table. This is the table I extract from the CBOK textbook. So this one actually they are online copy for the whole book. Okay, for the book, or I call ebook lah. But it is not the letters version, sufficient already. So you can find this one easily. Just Google around, then you can get, because I cannot share, it's illegal. So you have to, if not, then you go to library. They are hard copies, the book. You can actually, either you want to download or you go to the library to borrow the books, CBOK textbook. So what the title of the book, you refer to the MI. There is one section there, we have the main reference of this module. For all the modules the same. If you want to know what are the textbooks we are using, then you can refer to the MI, go to the reference there to check, okay, what are the main references, the books we are using for different modules. So for this module, we are using the CBOK textbook. Okay, so some recap. we have the function of t and then function of s. So last time in your Maths 2, I believe Maths 2, who teach you Maths 2? You
Dr.
can
Pang.
unmute. Dr. Pang, okay. So I believe that you roughly know the idea. It is a conversion between the T response, which is the time response, into the S response. So why you need the T response and S response? Because majority of the equation, they are represented using the S response. Just like you have learned how to solve the partial fraction, they are also in S. Like first order process is K over tau S plus 1. So they are in S response. But S response, it doesn't tell you the behavior of the process. Therefore, the S has no meaning if, let's say, you want to study how the process behave, the behavior, either it is stable or not, what is the final value, initial value, and so on. Therefore, you have to convert the S response back to the T response. So we have Laplace transform of Ft. Ft is any equation involving the time. Okay, it can be impulse. Impulse means 1. It's very fast. So once you Laplace transform, you actually get back the same answer for the impulse. If let's say your function of t is unit step means your Ft equals to 1. So when you Laplace your Ft, means you Laplace this 1, meaning that you will get the answer straight away. You refer to the Laplace table, you will get 1 over the S. So if your function of t equals to t, then your Laplace, this one, you will get, you will just need to refer to the table, Laplace table, to get the answer. So this is the one we call as the, you can get the answer directly from the Laplace transform table. So if let's say it's t power to n minus 1, then you will be using this one. So this is just like the Laplace transform of Ft, you get the Fs. So some recap, when you Laplace transform the Ft, you will get Fs. When you inverse Laplace the Fs, then you will get back everything back to T response. So this is the Laplace transform. And Laplace transform table, you only can refer when they are already in their simplest form, simplest. So in order to make it into simplest form, sometimes you may need to utilize the technique of partial fraction. You have learned this in one of the maths as well, meaning that you have to break them down into their simplest form. Only then you can refer to this table to find the conversion. So this is a direct conversion using Laplace table. Okay, so we will try few questions to let you familiarize how can you use this Seaborg Laplace table to find the answer. So we start from the A. So A is 3 over the S. So this one is inverse Laplace, meaning that you have to do inverse Laplace of 3 over the S to get back the answer in function of t. So from here, you will refer to the Laplace table to get the similar term. So 3 over the S. So in this case, you don't need to Laplace any coefficient of the term. So we will actually factorize the coefficient. Then we will left with this one. So you don't put the 3 inside, 3 is outside. So from here, the answer will be 3. Then for this term, you refer to the Seaborg table, 1 over the S. So 1 over the S will be, so I will clear the page. So 1 over the S is this one. Then the answer is unit step. Unit step means the answer is 1. So if I put in layman term, what is unit step? For example, I change a value by 1 unit. Like the temperature of this room, I changed from 25 degrees Celsius to 26. So the change is by 1 unit. So I apply a unit step change to the temperature of this room. So this is unit step change, means the change is by 1 unit. So from here, the answer, inverse Laplace will get you 1. So multiply with 1, you'll get the answer equals to 3. So done. So B, 3 over S plus 2. Okay, then you have to find similar one. So you will put Laplace, inverse Laplace of 3. We will have to factorize outside. It is a number. Then left with 1 over S plus 2. So you will need to search for 1 over S plus 2 from the table. So 1 over S plus 2, it is this one. So 1 over S plus 2 is 1 over S plus B. So the answer is e power to negative bt, where your B in this question, the B is 2. So you'll be having e negative 2t. So you copy this answer, you will get 3e negative 2t. It's a direct conversion. So because they are already in their simplest form, therefore you can straight away refer to the Laplace table to get the answer. So this is the direct conversion to get the answer. So B, done. Okay, C. 3 over S power to 3. So again, you will do the inverse Laplace of this, 1 over S3, and then 3 you will actually keep outside. Okay, so from here, you will get something similar to this one. So I will just screenshot this so the easy comparison. Copy. So we go here. So you have power to. So the one closer, similar to the question we have, the pattern, okay, the pattern is this one. Okay, so from here is t power to n minus 1. So the one we have is 1 over s power to 3. So you need to do a little bit of modification. Okay, so I will erase this one. Okay, you have to do a little bit of modification. N is equals to 3. So I will have something similar with this one. So the top must be having, when your n equals to 3, so it must be 3 minus 1 factorial over to s, and then 3. And originally, you're already having 3 outside, something like this. Okay, so 3 minus 1 is 2. 2 factorial means you have to 2 times 1 equals to 2. So this will give you 3 and then 2, then s to 3. So originally, you only have 3 over s3. This is the originally given. So from here, you do not have the 2 based on the original question given to you. Therefore, you have to do a little bit of modification. You have to divide by 2. So that when you cancel, you will get back the one originally given to you. So based on here, you will have final answer as, so this one, you already proved that this answer will give you the answer of this. Okay, so you still have the 3 over the 2 and then e negative, e t is t. So it's the term number 4. So it's t 3 minus 1. So it's 3 over the 2 t power to 2. So you have to do a little bit of modification. So what you can do is you always find the one closer to the one given to you. Originally given is having the 3 here and the s power to 3. So I keep the 3 here and also s power to 3 here. And then I will need to check the one given to me on the top must having n minus 1. So I should follow n minus 1 here. So this is the one I have to fulfill this term. So I have to fulfill Okay, I need to erase. So I need to fulfill the one given over here. You don't have, so you have to create one, 3 minus 1, then factorial. So because of you are having this one, like this, so meaning that is 2 times 1. Originally, there is no 2 factorial over there. Hence, you have to do some modification. When you create this, you have to remove. Then it can go back to its original form given, which is 3 over s power to 3. So in this case, this is the direct conversion. So the one here is a direct conversion. 2 factorial over s3 is a direct conversion of this term. 2 factorial s power to 3. Then whatever remaining will be its coefficient. So I bring them down. Then this one is from this. Then you will solve the answer. Finally, 3 over 2, p power to 2. So this is C. Okay, D also you have learned in Maths 2 as well. So if cannot copy this one is fine. Later on, this written copy will be shared to the Telegram. So some of you didn't know why I share some of the PDF there. Actually, that one is in the live section we have. I share with you so that you can have it for your revision purpose. Okay, if let's say you cannot copy, no time to copy that time. Okay, so go back to question D, 1D. So D, s plus 4 over s power to 2 plus 4s plus 8. So always you have to make them into the simplest form. So when you have this one, what can we do is we try to perform some maths. Like for example, okay, you must refer back to the Laplace table so that you will get the idea how it looks like. You are having s power to 2, then the other side having something there. So you refer to the one, the closest we have is these two. If you check from the rest, you do not have the s power to 2 plus whatever you have. So you try to link to the pattern of these two. So I will copy this. Term 14 and 15. Then we will utilize this one so that we can modify the whole thing closer to the pattern of this. So in this case, the bottom must having the denominator must be having omega square. So meaning that you have to do the how you say, you have expansion, then you have to factorize. So it'll be s plus 4 over the maths you have learned is s plus 2. I do not remember the technique of this one. So it's plus 2 squared. So this one is maths. How you simplify them so that you'll be having s squared and then plus omega squared. You want to change this one to s squared plus omega squared. Okay, so when you do the expansion, you can actually get back the s power to 4, which is this one. When you do the expansion of this, you will get back this. So there is a formula to get this. Please do your own revision. This is a simple maths. So when you have this already, you have to split them into 2 parts. So you'll be having s over s plus 2 square plus 2 square plus 4. Means you split this one. And then you can decide which one you want to use. Like for example, you have the s term here. This will bring you term 15. This one is a number. And the number, in this case, it must be same with omega. Your omega is 2. So what can you do is, you have 2 there, so it can be s plus 2 plus 2. so that you can having this one group together. Then you will having omega is 2 because we want to fulfill the same pattern. Omega is 2. So if this is 4, cannot. So you have to redo. This is wrong. You have to S over S plus 2 power 2 plus, this one is plus 2, meaning that we have to use this one. Then 2 over S plus 2 power 2 plus 2 power 2. So you have to do the multiplication based on the one given to you. Like for example, term 14, if I follow the first one, I can't get the answer because the W is 4. The W here must be same value with this W omega lah. So you have derived this as 2. So your omega is 2. So I will put a color here. This is your omega value. So this one is omega, but it is not equivalent to 2. So cannot be used. Your omega or W must equal to 2. Therefore, I have to redo. My answer will be the purple color, so that this will be the term I can use. So this one will be in bracket. So in this case, this form is again term 15. This is the term. So this one is S is 15, then 14. So based on here, you can continue to solve the one you have learned. So I have a recap, put a note there. You have learned something like your Maths 2 theorem. So there is one of the theorem that say when you have inverse Laplace of function, and inside you have S plus minus, let's say I use the K lah, then the answer is Laplace of this, you will get E negative plus KT FT. Okay, so this theorem 1, 2, 3, 4, I remember you have few theorems from the previous Maths 2. Please go to print out also that copy because the theorem 1, 2, 3, 4 will be given actually during your final or test. So in this case, this is the theorem we are going to use. So based on here, you will find out that your K is actually 2. And this is the plus sign. Then you are going to use the negative sign. So 2T, then FT. Okay, so I will go back. I will go to the next page. So I will put it down here. So finally, you will get, okay, I will copy again. So your final answer will be E positive become negative. Your K is 2. Then this is term, your S1 is term 15. So term 15 is cos WT. So it's cos W is 2T. Then this is term 14. Your term 14 is sine omega T. So you already have E negative 2T again, and then sine 2T. So why you have this? It is because of the theorem of Laplace of F. If let's say inside you have something plus minus K, okay, then the answer will give you E minus plus KT multiplied with FT. So this is the revision. I can't remember which theorem is this. When you have function of S plus minus a number, then the whole thing, when you inverse Laplace, you will get the exponential term multiplied with the FT. So how to get this FT? Your FT is actually the inverse Laplace of Fs. So this is the recap A, B, C, D for question 1. Okay, so I give you some time to copy. So we'll move on to question 2. If you only focus on the tutorial for your revision for test or final, It is not sufficient. I think I mentioned a few times already. The examples or questions are also in your lecture slides. So don't forget about your lecture slides. If you compare the lecture and also the tutorial for this week, right, there are more examples provided in lecture instead of tutorials. So your job, you have 10 hours per week per one module. So when you minus the 4 hours we have for lecture and tutorials, you're supposed to have 6 hours of revision for each module. So that 6 hours will be the time you spend to complete the homework I give to you on weekly basis, and also do your revision for your lecture as well as your tutorials. Then you will know how many examples or questions we have discussed based on the lecture and tutorials. That will be the examples you need to do the revision for your test and final. So don't just focus on the tutorial question, not sufficient. Okay, so this is the question 1. So question 2. When you want to Laplace transform a differential equation, then the one you need to focus will be term 24 and 25. So you can copy and paste the term 24 and 25. So when you have the Laplace transform of df over dt, then the direct conversion, so this one, Laplace transform of df over dt, will give you the answer based on the direct conversion as fs minus f0. Same goes to this one, will give you the conversion of this. So this is differential n order derivative equation. So from here, this will be the one we have. So you can see here have 3 terms, 1, 2, 3. So you have to do the Laplace transform of all of this. And remember, you have to Laplace the both sides. And UT is the unit step. Step unit. What is the name already? It is a unit step. Yes. So this one is a unit step, meaning that it is 1. So when you Laplace transform 1, you will get 1 over s. So equals 1 over the s, one side. When you Laplace transform this, you will get 3, a big one, ss. So now you can change, like for example, if you can link, right, the symbol f now, it is actually the symbol of x. So if let's say you Laplace the x, you'll see function f will be using capital. That's why this is a small letter. After you Laplace it, this one will become capital or uppercase, capital letter. Then you'll be solving here 3 big one s. Just like you Laplace your f, you will get the answer of fs. So understood, this one is actually 3xt. Just like they give you this one, it means t, because the whole equation in t response. So Laplace of x is actually function of t. So after that, you will get this. Recap. Okay, then this is the first order. First order, you have to use this s fs minus f0. So from here, the conversion, just now, they are not using letter of f. In here, your x equals to big X, sorry. Your x equals to small f. Your big X equals to big F. So if let's say I want to have 4 dx over dt, Laplace transform of this, I will get 4s(xs) minus x0, this one. So I will be just changing the letter of x to f. So x to f, x to f. Interchangeable. Okay, and remember to put a bracket here because a 4 is outside. So this is term 24. Power to 1. So this is term 24. And now this is term 25. So term 25, you'll be using this one. So I will just copy page and then maybe paste the page. Okay, this one. Then I erase everything. Page. I should erase like this. And then, okay, give me some time. I don't know how to change the figure to background. Let me learn next week. Okay, so now the one last term is this one. D power to 2 and then dt squared. The Laplace of this one will follow this. Okay. So I will have S, your n is 2. So here, 2. Then xs minus s, 2 minus 1. Then x0 minus s, 2 minus 2. Then x derivative, first order, then 0. So if this one already give you S0, then you should, S0 equals to 1, right? Then you should straight away, you can just left with only this term. Because S power to 0 equals to 1. Here actually having S power to 0. So the last term will be x2 minus 1, 0. So when you simplify this, you'll be having S2 SS minus S power to 1, don't need to write, then x0 minus, and then I just put that so that you won't get confused. S0, x derivative, 0, and lastly, this one also nothing there. This is a repeat one already, so you cannot do anymore. So this one cancel because this is the same one, same like this. Okay, so x prime 0. So I will erase this. Okay. So 2. So the last one is x linked s prime 0. So this is the last one already. Why? It is because when you have s power to 0 is 1, meaning that it is actually the last term of this already. So this will be the last term, meaning that there will be no other term after this. Because here indicate your s already power to 0. Yeah. So you have to stop. So where to stop is to check the last term. Last term is s power to 0 here. So when you get s power to 0, you have to stop. Means finally, you will get the s power to 0. Start from the highest order of s. Let's say you have s5. So 5, 4, 3, 2, 1, 0. Then you stop. You have learned this in your Math 2. Okay, so we recap. If you still need more examples, I think they provide you some of the tutorial questions in your Math 2. You can go back and try again. Okay, so then you combine everything. So this is the one we call as the initial condition. X is just like a parameter. For example, height. It can be the level, it can be composition, it can be the temperature, for example. So the initial condition given equals to 0. So in this case, this one equals to 0, this one equals to 0. So you combine everything, you will be having S2 xs minus 0 minus 0. Okay, now we have 3 terms, right? So the final answer will be, let me combine everything here. Do I combine? Okay. So your answer will be S2 xs plus, and the second term just now we have the 4 outside bracket SSS minus x0 plus 3xs. You Laplace transform both sides. So this one also 0. So now you have to factorize the SS. So factorize the SS means simplify the equation. So you'll be having s power to 2 plus 4s plus 3 bracket xs equals to 1 over the s. Now you will see something very similar with partial fraction. Okay, so you'll be having your output, you remember one of the rule, you have to move your output to the left-hand side and the rest to the right-hand side. So you'll be having 1 over the s, and the rest will be s power to 2 plus 4s plus 3. So this one have to solve using partial fraction. So you can see the control module, you need to have a strong maths background. Sufficient to only learn maths 1 and maths 2, you can survive in this module. But if you couldn't score well in maths 1 and maths 2, you have to do your own revision. Go back to maths 1 and maths 2, study back the techniques we have. For first week, only the Laplace transform, partial fraction, and also integration method for the first week. Okay, so based on here, how to solve this using partial fraction? You have to split them into the form like, for example, if you can simplify this, you have to further simplify into 1 over the s, and then s plus 1, s plus 3. Okay, so you're having 1 over s multiplied with s plus 1, s plus 3. Why you need to perform partial fraction? So maybe previously when you learn maths, you don't know why I have to solve using partial fraction. So now for CE student, you can link better, you can know better. Oh, the partial fraction actually is to break them into their simplest form. And then you are going to use the Laplace table to do the direct conversion. So based on here, you'll be having A over the S plus B over S plus 1 plus C over S plus 3. So if you totally forget what is partial fraction, you have to do the revision. So this is why when you come for the tutorial, you cannot be so busy copying everything, but you have to open your ear, listen. The one I mentioned, important, this one you have to do, is the notes you are going to take. Like just now, Aaron mentioned many significant things you have to do your own revision already, right? So the final answer, to copy from the beginning until the end, the solution is not important because the whole copy will be shared later to the Telegram. So just now I say partial fraction is very important, right? It is important because we want to get the simplest form so that we can refer to the Laplace table to get the answer. I think this sentence is more important than the solution over here. Then I say you have to go back to your maths 2, study back the theorem 1, 2, 3, 4. I think that one is more important than the solution based on the previous question. So sometimes you have to listen and multitask a bit lah, huh? Don't aim to copy the whole question solution during a tutorial, but to jot down the important information. So this is the skill, learn smart. So this is week 1. That's why I give you some tips of learning. I believe some of the lecturers also share with you lah, how can you learn smart? Okay, so now is partial fraction. Partial fraction have 2 methods to solve, but first of all, you have to do the expansion first. So you'll be having 1. Then you multiply all of these to the other side. So you have to multiply 3 times to here, to here, to here, right? So you will get the 1 equals to A S plus 1. So originally you only have S. So you'll be having S plus 1 and S plus 3. Then B. You already have S plus 1. So it will be S plus 3. Then C. You have S plus 3 already. So left with S. Okay. So there are 2 methods to actually solve the partial fraction question. So one of it is do the expansion. And then you find the coefficient, compare the 2-side equation, you can solve all the ABC. The other one is make the one of the term disappear. So how to make this term disappear? You can try with S equals to -1 or S equals to -3 or S equals to 0. So the idea is you have to make the term disappear so that you can simplify and get the answer. So if you have A, B, C, 3 unknowns, then you must have 3 values of S. If you have 4 A, B, C, D, and then you must have S1, S2, S3, and S4 to solve all the A, B, C, D. So let's say I put the S equals to -1. So you just sub in all the equation there. You have solved the A equals to, so now I'm solving B. So I won't show you the full step, but the idea is more important. So you will get the B answer over here when you sub the S equals to -1. So what is the important point I want to deliver here is you have to think of the values of S. How many values you need to think of? If A, B, C, then 3 S value. What are the 3 S values you are going to use? So the 3 S values you are going to use will be the one making the term disappear. Just like when I have my S equals to -1, the whole thing will multiply with 0, gone. If I have S -3, then this whole term will be 0, disappear, gone. Same goes to if I have my S equals to 0, then this whole term will be gone. So the idea is to make the terms gone, disappear. So when I have the S equals to -1, I will be solving to get my answer. B equals to -1 over 2. If I have my S equals to 0, then I will be solving my A equals to 1 over 3. Then S equals to -3, I will be solving my C equals to 1 over 6. So you have to perform this simple calculation your own. So the revision time 6 hours per module is to complete the tutorials. At the same time, do your own notes and keep for your test, revision, and also your final exam. You don't do your revision at the end of the semester or nearer to the test. You have to do your revision, your notes, your summary of the week 1 per weekly basis. That's why each module you'll be having per week 10 hours. Of course, the 10 hours won't include your travel time, rest time. So the pure 10 hours per week will be the 2 hours of tutorial, 2 hours of the lecture, and then 6 hours own revision. So you do your calculation. If you have 4 modules, right, you'll be having 40 hours, excluding your travel time, excluding your lunch time, excluding your play time, date time, whatever time, 40 hours. So do your own timetable. I have to give you advice at the beginning of the semester. Semester 4 onwards, all the modules, they are mainly core modules. They are very difficult modules, very comprehensive, very challenging. If you compare the modules you are taking now to the modules you are taking previously. The previous modules, they are fundamental modules. If you study, you do a tutorials, you can score A, but not for semester 4. Semester 4, the question given to you can be just modified a bit, become a new question. So you really have to know the concept, then only you can score for all the modules in Sem 4. For example, fraction, control, CETS, mass transfer. So that's why I don't advise a student to take too many core modules in Sem 4 unless you want to transfer. If no, you have the combination of 2 core modules, 2 electives. Okay, I think I repeat this one a few times. So next, so once you have this already, you have to put it here, right? So you'll be having your answer of 1 over 3 multiplied with 1 over the S. So I won't actually put my A on the top. I will actually move the A outside. So originally it's A over the S plus B over the S plus 1 plus C over S plus 3. So my A answer just now is 1 over the 3. B is negative 1 over the 2. C is 1 over the 6. So you can see I put my A actually outside so that I can have my 1 over the S there. So B also I put outside 1 over the 2, then 1 over S plus 1. I will put bracket, easy for me to find the simplest form. Then all of this is just coefficient. Then plus my C answer is 1 over the 6, S plus 3. So inverse Laplace of this is a direct conversion using the Laplace table. You will get the answer in xt. So just now, all the final answer, it is in t response. So it is xt. So just now, the few questions we have already, right? So all of these, so just now, we don't have it. This is the second question. So now we have 1 over 3. Inverse Laplace of 1 over the s will give you 1. Negative 1 over the 2. And this one will give you the answer of e negative 1t. So we do not write the 1 there. So it will be just e negative t. We don't include the 1 there. Okay, and then plus 1 over the 6. Then we will have it e negative 3t. It is the similar one. Not similar, it's exactly the same one. Just one is 1, the other one is 3. So e power to negative 3t, e power to negative 1t. So I will erase the 1 here, negative t. So this is the final answer. So the second question, having few things you have to do your own revision. Let's say you think, I cannot follow during the tutorial section. You have to go back for your maths 2, go back to your maths 2, and maybe your partial fraction and Laplace transform. And remember in the last lecture, Monday, I mentioned that you have to do your own revision about heavy side as well. Heavy side. So these are the things you have to take note. Okay, that is more important than copy the answer during a tutorial. I believe that if you just copy the answer during a tutorial, after the session done already, you are blank. Okay, but you have to jot down the important information. So this is question 2 already done. So we now proceed to question 3. Okay, question 3. I do not include values inside. So this question, let's say I want to convert, okay, change to test question or final examination questions. I just need to include numbers. Okay. So from here, the control module, it is challenging. It is because of, it is not just one module you need to focus. In order to score for this module, you maybe have to have a strong fundamentals in mass balance, or also thermodynamics, some core modules, and also physics. Just like this example, before we talk about the control, it is just the fundamentals you need to derive based on some basic concepts, how to derive the equation, what is ideal gas law. So let me read the question. So consider a liquid flow system consisting of a seal. Okay, so this one to take already. Yeah. Okay. Okay. How can I choose? Okay. Okay. So it is a seal. Seal means everything is there, nothing escape. So this is a seal. With non-condensable gas above. So meaning that the gas will be here. It won't dissolve or go inside the liquid. Non-condensable means the gas will be on the top layer. So the gas won't be actually dissolved in the liquid. So this is non-condensable gas. It will be always a layer of gas above the liquid. So this is the definition. derive an unsteady state model relating. So where I cut all this, relating the liquid level H. So you are going to derive H as a function of T to the input flow rate Qi. So means this is your input. Your Qi is the input. Is the operation, okay, I don't know why they cut so much. Is the operation of this system independent of the ambient? Is this operation ambient pressure PA? Okay. What about for a system open to the atmosphere? So you can make the question simpler by giving assumptions. For example, ideal gas law, a constant amount of mg over the total, which means m, moles of gas are present in the tank. The operation is isothermal. It means you don't need to consider about energy balance, because temperature is constant. There is no energy balance. A square root relation holds for the flow through the valve. So meaning that this one is related to the temperature drop, delta P. So in this case, your delta P here, it will follow the direction of the flow. If let's say it goes this way, meaning that your PA is greater than the pressure at the bottom of the tank. So if let's say this is the still one, you'll be having at the bottom of the tank, what will be the pressure, total pressure. So the total pressure of this one will be contributed by the by this liquid and also by this layer of gas. So we'll be using a lot of fundamentals to finally derive this equation. Okay, so I will go to the next page. So this is the question about, they are asking, one, you derive the equation for the sealed tank. If let's say now the tank is no longer sealed, it is open to the atmosphere, means I remove this. What will be the model? So you have to derive two times. One is for the sealed tank. Second is for the open tank. So from here, equations are given for the flow rate, exit flow rate. And they say you can use ideal gas law and you can use a constant mg over the m. So if they say the mg is constant, when you have dmg over dt, mg is constant, it will give you 0 because mg is constant. So if mg constant, if you do this dmg over dt, it will give you 0 because mg is a constant number. Okay, so I will solve this. So based on here, first thing, think of the concept. Every time you want to derive an equation, you will utilizing conservation of law. You will be having mass balance, you'll be having composition balance, you'll be having energy balance. So based on this simple example, composition is not given, temperature is constant, hence you only have mass balance. So mass balance means the general equation we are using is dm over dt equals to mass rate in minus mass rate out. So in this case, the mass inside the tank will be having the mass of the liquid and the mass of the gas. So we'll be having dml plus mg over dt equals to what is going in. So the one going in, I will just highlight here, going in, this one going out. Is the gas going in or is the liquid going in? Liquid. The gas is there at the beginning already. You do not transfer the air going in. So all of this mass in and mass out, they are referring to the liquid. Liquid going in, liquid going out. So they'll be having a mass rate involving the flow rate, volumetric flow rate. So how you derive something multiplied with the flow rate? You just have to multiply with the density. So this will give you, for example, mass rate. Because concentration is not given, they're supposed to give you something density. So if it is a test question or final exam question, I will say the density of the liquid is given by a value. Then you will know this mass rate you should relate. It will be the product of density multiplied with the volumetric flow rate. So this stands for volumetric flow rate. So the in will be rho Qi. And the out will be rho Q. Okay, so from here, just now we already know mg is constant. So we are only left with dml over dt because dmg over dt will equivalent to 0. So this equation will left with dml over dt equals to rho Qi minus rho, and the Q is given as CV delta P. So you have learned 1C in the previous lecture 1. CP stand for heat capacity. This is CV. CV is the Watt coefficient. So this is a Watt coefficient. Okay. M equals to rho V, correct? But this is regarding the liquid. So it will be volume of the liquid. You see L. So I will expand ml. What's my ml? It will be rho VL. So from here, I'll be having rho is constant, so I factorize outside. I'll be having d VL over dt. That equals to rho Qi minus rho CV delta P. And then what is your VL? Volume of the liquid will be A area multiplied with the tank level. So A is constant. Therefore, you'll be having rho A dH over dt equals to rho Qi minus rho CV delta P. What's a delta P? Your pressure drop will be, if I draw a valve over here, this one is exit flow. So it's here. Outside, you are having PA, atmospheric pressure. Inside the tank, this one will be a combination of these two components. One is liquid, one is the, so I put P gas and PL. When you have direction of flow go here, so your PA, your delta P is the one you learned, I don't know which module already, pressure drop. So the pressure drop meaning that this point must be greater than PA, so that you'll be having a direction from the tank to outside. So in here, you'll be having your PG plus PL. At the bottom of the tank, the pressure is the highest. This is physics, right? Thermal physics. So how you actually get the pressure at the bottom? It is the pressure of the liquid plus the pressure of the gas. So minus the atmospheric pressure will give you the pressure drop. So this one is the one you need to submit here later. So now they say PG, you should relate to the ideal gas law. So this PG will be using the one you have learned previously, using the PV equals to RT, remember MRT. So this is about the gas. So ideal gas law will give you pressure PV. So we move the V to the other side. Okay, some recap. Okay, so I will go to the next one. So ideal gas law, you'll be having PV equals to, if only gas, you'll be having gas over the total M, MR, gas constant, then temperature. So, and the V, you should expand. So this is about the G lah. Okay, G. So this one should be related to the G as well, because we are talking about the gas pressure. So we're having your PG equals to mg over the mRT over the VG, right? So if you look at the tank of this one, let's say the whole thing, I can't remember what they draw. The whole thing is H, and then the liquid level is H, small h and big H. So I'll put here. So the big one is H, and here is your H. So what is the height of the gas? It will be H minus small h, where you'll be having mg over the big M, RT over volume of the G is cross-sectional area multiplied with the H minus H, which is the gas. It's about the gas. Then you'll be having A, and then H minus the H. So when you combine everything, so I will be having rho A dH over dt equals to rho Qi minus rho Cv, and then bracket whole thing, mg over the mRT over A layer of gas plus, okay, what is the pressure of the liquid? Pressure of liquid is related to rho Hg. And this H is the level of the liquid, rho Hg. So you'll be having rho Hg, liquid. So this one is actually pressure of the liquid. So at this point, you'll be having Pg plus PL. The total of this minus ambient temperature will give you pressure drop. Okay, this is why we want to expand. Okay, and then minus PA. So this, all of this inside is actually delta P. Okay, so you cancel your rho, then you will get the simplified equation already. So it'll be A dH over dt equals to Qi minus Cv, then the rest follow the same. So this is the model we actually not yet derive or solve until the end. So imagine if numbers are given, they only need to give you some initial condition, then you can further solve using integration method to get the ht, h as a function of t at the end. If all the values are not given, just like this example in tutorial, then it is sufficient to stop here, nothing to solve further. So this model is dependent on PA. It is because of PA is here. Okay, so if let's say this is not the seal tank anymore, so what you need to change will be, okay, I will use different color. So if let's say, okay, I will just copy the whole page to the next page. So copy. So maybe this one, okay. Yeah, no. Page. Okay, so let's say this is no longer sealed. So I'll be having something like this. Okay, so when you have this point, the changes, I will just put red color. Your PL will remain the same, rho Hg, yes, but your Pg will, when you have non-seal, meaning that the gas will escape. Right? It will escape. And the whole thing is also suffering. No lah, they also have the PA over here. atmospheric pressure. I don't think the gas will stay there if it is already open, right? So the gas, the layer of the gas on the top of the liquid will escape, right? But it will be atmospheric pressure acting on the surface of the liquid. So now your delta P will be, at this point, you'll be having your PA plus PL, right? PA plus PL. Okay, and then you'll be having here also PA. So the pressure drop will left with PA plus PL, and then outside is PA, correct? So when you have unsealed tank, this one will run away, escape. The atmospheric pressure will act on the layer, surface of the liquid. So this one. So at this point, you have to consider this and also PL. So you will have this. And the direction of the flow still follow this side going up. So you'll be having this one modified to be cancel this, become PA plus PL minus PA equals to delta P. Hence, your answer will, the PA cancel out, will only left with pressure of liquid, where your PL is, you expand it, it will be rho Hg, done. So you'll be having this one, if open tank, you'll be having A dH over dt equals to Qi minus Cv. Then we're having rho Hg. Because these two will cancel, plus PA minus PA. The rest follow exactly the same. And for this, you do need to consider Pg. Gas will escape. Okay, so from here, no, it will change to PA. So I will just make it easier. PL. Okay, so once you have this, actually you can cancel out already lah. So the final answer is left with the PL, which is rho Hg. Why? You can sketch this, put some notes there, gas will escape, but it will be having PA act on the surface of the liquid. So that's why the pressure drop over here at this point, it will be a total of PA plus the level, the liquid pressure rho Hg. It is going out, so you have to minus the PA ambient, the atmospheric pressure, so that it will give you the delta P. Delta P is the pressure drop. So if it's too messy, then maybe you can draw one more time here. When you have this point, layer, so the one acting on this one will be PA. The flow of the liquid is going out, here is your PA. So this point will be PA plus PL, where your PL is actually rho Hg. So if the direction is going this way, so your delta P will be the total of these PA plus PL minus this one, PA. Okay? So this one is for open tank. So the question is the model dependent of PA? Then you will look at the final answer. There is no PA in the equation. So I can say this is independent of PA. Because the PA is gone in the model. So this is question 3. Then we will have a break. 5 minutes, 5 minutes. We only have like 2 more questions left. I think I can solve in half an hour for that too. So we break for 5 minutes, then we can leave early. Yay! Okay, another reminder, please download, install your MATLAB. We are not going to campus to do our MATLAB. We will have our MATLAB at home as well, the week 5 and week 6. And week 5, week 6 also will be in your test 1 scope. It is because of test 1 do not request you to run your simulation, but I will request you to sketch the block So you won't know what is block now, but by the time week 5, week 6, you will know the simmering blocks. So we will rest for 5 minutes. Then we come back. At the same time, I will share with the camps. So we have full attendance. No, yes, no. I think one absent. Okay, maybe I go here. I don't know whether I can online or not. Refresh.
Nigga, I have no idea. I'm so lost. I'm fucking lost.
Give me some time. I change to other network is shared. Oh,
What?
okay. This also I changed to 2.4. Wait a while. Can you all see the share screen? Yes, no? Cannot. Let me think how to solve this. This can't rejoin. So, share screen, share the screen. Okay. 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 Okay.
Bro, even the code is saying it's fuck. No 4896, right? In Cantonese,
Okay, then we
yeah,
break for 5 minutes.
4896 in Cantonese means sibei gao lat. It's like you're fucked basically. Even the code is fucking for real. How can? How can? I don't know lah. I'm so done lah. I'm so fucking. Bro, this is ANSYS all again, man. We learn A, we do B. Fuck. Okay.
Anyone not able to mark the attendance? I think everyone already done, okay?
Wait, I think right.
Okay.
I think she forgot to record just now. Luckily, bro. Oh my. Oh my god, this is so fucking scary. Leo, how can? Ay, then I'm gonna record myself lah.
Continue. Okay, question 4.
Not bad. Not a bad business idea.
Okay, come on. We have two more. Two more. Also simple question. Boring. Okay, so question 4. So you have temperature given. So whatever question given, you should always start with the mass balance and then check whether composition given or not. So for this question, composition is not given. So there is no composition balance. Temperature given. So you'll be having energy balance. So for this system, a jacketed vessel is used to cool a process stream. So you can see the liquid in the tank and the liquid in the jacketed vessel, it is not mixed, meaning that you are having two systems. One is the jacket, the other one is the tank. So the liquid here, it is the coolant. It is because they are used to cool the process stream. So this is your process stream. The flowing information is available. The volume of liquid in the tank, so this is the V, and the volume of coolant in the jacket is a V, then letter J, remain constant. So in the lecture, we learned already, if volume remain constant, you'll be having dV over dt equals to 0. If no, then you maybe have to solve using the chain rule, and we have covered the chain rule in the lecture slides already. So in this case, volume is constant, then dV over dt will be 0. It is because of volume is constant. Same goes to dVj, the jacket over dt, also 0 because V and V jacket both constant. Okay, then volumetric flow rate QF. So here is your QF is constant. So QF is constant, but QJ varies with time. So QJ varies with time. Okay, this is the first one. Heat losses from the jacketed vessel are negligible, meaning that the heat transfer only involves the hot fluid, which is the process stream, and the cold fluid, which is the jacketed vessel, the coolant in the jacketed vessel. The heat exchange is in between these two, cooling medium and the hot fluid. There will be no heat loss to the surrounding, no heat loss. Both of the tank contents and jacket contents are well mixed. So this means at any point in the tank, any point in the jacketed vessel will remain the same temperature. For example, the temperature of the tank will be T. Jacketed vessel is Tj. So this is called well mixed. The temperature will remain constant at every way. in the tank or in the jacketed vessel, the T and TJ, there are two different temperatures. What I mean everywhere is in the tank, the T will be the same. In the jacketed vessel, then everywhere will be having the same TJ. So all of these will be having same TJ, same TJ. So this is so-called well mix. Okay. And have significant thermal capacitances, meaning that you cannot remove the heat transfer mode contributed by the heat capacity. So we have three heat transfer mode. One is conduction, one is convection, one is radiation. When they say heat capacity is very, very significant, means if compared to the rest, these two are not significant. Because the H is not given, the radiation parameters are not given. They already mentioned the one super important is only the heat capacity. Heat capacitance means for the cooling fluid and also for the process stream, the hot fluid and the cold fluid. It means you only need to consider conduction because of CP is significant compared to the H, convective coefficient, and compared to the radiation. So from here, you only need to focus the energy balance derived from the conduction, heat transfer mode of conduction. Okay. The overall heat transfer coefficient for transfer between the tank liquid and coolant varies with coolant flow rate. U, you have learned U, right? So in thermodynamics, U is when you have the heat exchange of two mediums or two like cooling fluid and heating fluid, for example, hot fluid and cold fluid, and they are not mixed together, just the exchange of heat. So the U stands for the overall heat transfer coefficient. So U is overall heat transfer coefficient. So if you have higher U, heat transfer coefficient, means there is a greater heat exchange between the cold fluid and also the hot fluid. So, okay, so from here, the cold fluid is the one in the jacket. The hot fluid is the one in the tank. So the jacketed vessel is just to cool down the hot fluid inside the tank. So the U is given in with this equation. And U stands for the heat transfer coefficient, then QJ and the K, there are some parameters given. So they want you to derive the dynamic model for this system. There are how many systems over here? Two. One is the jacketed vessel, jacket. The other one is the heating tank. So you are going to derive two equations to represent one for the jacket and one for the tank. So if it is a jacket vessel, you always have to remember there will be a heat exchange. Either you absorb the heat or either you release the heat. So for example, this is the jacketed vessel. It will absorb the heat from the process stream because process stream is hot. So this will having plus, the sign of plus because of heat absorption. And for the process stream, it is a hot fluid at the beginning. Then there will be a heat rejection. So to indicate heat rejection, you have to put minus. So plus minus, it is just the heat transfer between the hot fluid and cold fluid. So you'll be having UA delta T equation that you have learned in the previous thermodynamic module. So this is a heat exchange between the hot fluid and cold fluid. Heat exchange, one is absorbing the heat, then you have to put plus. So plus, you have to put for the coolant. Negative, you should put for the hot fluid, which is the process stream. So you can put a note there. Why coolant is positive? Because coolant is absorbing the heat and the process stream, hot fluid, is releasing the heat. So this is a heat exchange. One absorbing, The other one is rejecting the heat. When you absorb the heat like coolant, you have to put plus UAT. If the process stream in the tank, it is releasing the heat, then you have to put minus UAT. So in this case, you have to derive two equations. We will start from the tank first, okay? So the tank. So in this case, the tank is releasing heat. So we will having energy balance. So in this case, they give you, they do not tell you the mass rate, right? W, not given. So if you remember the one we had derived in the lecture slides, dm over dt equals to W in minus W out. So if I'm talking about the tank, okay, if I'm talking about the tank, the W is not given, but you can relate the mass rate, which is the W, using the parameters of rho multiplied with the volumetric Q. So in this case, if let's say this is a tank, then we'll be having rho of the tank, they are using just the rho. Okay, and then the Q going in is QF, this one. So QF. So the in will equals to the out. It is because of volume constant. If you remember this, V of the tank constant. So you'll be having M equals to rho V. So dm over dt equals to d V, rho and V constant. So you'll be factorize rho V outside. So anyway, I just put in this way. Will give you 0 because rho and V constant. So if you have this, then you'll be having W in equals to W out. So if put in the context of the tank, the in will be rho Q equals to rho Q. So if I erase this one, too many things there already, I erase a bit. Ding, 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 ding. The out is here. So for the tank, the in is QF, the out is Q. So you will put QF, and then the out is Q. So in this case, the density will be the same, right? Because same liquid. The process stream is the same process stream. So you already proved that QF equals to Q. The inlet volumetric flow rate will equal to exit volumetric flow rate. That is why in the final equation, we will not having QF and Q, but all will be using QF. So this one will be straight away, I'm using QF. How we prove this? We use the mass balance. We use the volume is constant. We prove that mass rate in equals to mass rate out. And mass rate equation you can derive using density multiplied with the volumetric flow rate, which is this equation. So I'll put why I need to perform this, because I want to prove Q in equals to Q out for the tank, which means that QF equals to Q. This one for the tank. Finally, your Q also all replaced by QF. Use QF. Same goes to jacketed vessel. So if you look at the jacketed vessel over here, they also tell you something like volume in the jacket vessel. Jacket is also constant. So in this case, you'll be having V subscript J, so Vj. So it will be exactly the same equation you're going to derive, right? So for the jacket, the in equals to out. It is because of Vj is constant. Same goes to rho J just now, because jacket, they use everything subscript J. So in this case, you look at the jacket, the in is Qj, the out Qj as well. So they straight away give you but you can actually prove using the mass balance in equals to out. That's why Qj in equals to Qj out. So all these just to prove the volumetric flow rate in and out are the same. For the tank, in and out the same. And then for the jacket, in and out the same. It is because of V and Vj constant. So that we can prove two things. In and out, the flow rate will be constant. Q in equals to Q out, the summary. Then you break down into the tank, you break down into the jacket. Then we can prove the one I put in the box. So Qj equals to Qj, the other one is Qf equals to Qf. So this one for the tank, this one for the jacket. Okay, so this is not in the solution, just a recap when volume is constant. So now talking about the tank. So look at the tank over here. Energy balance will be simple equation dE over dt equals to E dot in minus E dot out. Energy rate in minus the rate of energy, the exit. So from here, and of course, it is not one system. There are two systems. If it's only one system, then this equation solved, done. But this is the exchange of heat between two systems. Therefore, you need to include overall heat transfer coefficient minus UAT. It is because of the temperature, it is because of the process stream is releasing heat. Heat exchange, one absorb, coolant absorb, process stream initially hot, it will release the heat. So that's why it is negative UAT. And the U is given as this. So the U later you can sub in U equals to KQJ power to 0.8. This is your U. So the temperature of the tank is given as the big T. So big T, correct. So U already there, A is the same, cross-sectional area of the tank. So if cross-sectional area of the jacket, you will put A subscript J. So this stands for the cross-sectional area for the tank. For the jacket, then you have to change the A to AJ. So they say heat capacity is more important, so you will be just using the conduction. So for whatever mode you have for D over dt, you'll be having M heat capacity, then your control variable is dt, your output, because your tank is T. Your tank is T. If your jacket, then it's TJ. Okay, so now we are using dt over time dt equals to the in. So the one going in is this. Okay, and the one going out from the tank is this one. So the inlet temperature is TF. Inlet volumetric flow rate is QF. Exit temperature is T. Exit volumetric flow rate, you have proved just now, is QF because of volume constant. So volumetric flow rate will be the same. So you'll be having in omega will be expand using rho Q. So I will straight expand from here. Oh, never mind, I just put one more sentence there. So omega Cp, so this one is the in. Then the inlet temperature is TF. Exit temperature, this one is W out. Cp will be the same because same process stream. Then exit temperature is T minus UAT. Then you expand the W equals to rho Q. So this equation will be rho, and then the Q using is for the tank is F. F Cp Tf minus rho Qf Cp T minus UAT. So M Cp dt, and the m also you can expand. Rho equals to m per v, m equals to rho v. So this is the v of the tank, they are using v. So m equals to rho v cp dt over dt equals to all this. So exactly the same equation you derive, but now you will derive for the jacket. This equation will be rho of the jacket, volume of the jacket, Cp, I put the J there, stand for the jacket, because the liquid are different, it's coolant. One of the liquid in the tank is, this is the tank heat capacity. Because they do not give you the heat capacity, how you differentiate C. So I will put one is C, the other one is Cj lah. So here I will follow everything the same. They do not put any subscript for the tank, so I will just follow Cp. Just like your rho stand for the tank density, your C stand for the heat capacity of the liquid in the tank. So now talking about the jacket, then I will just include the subscript of J to indicate this is the heat capacity of the coolant in the jacket. Then the exit temperature of the jacket is Tj. So Tj dt equals to everything the same, but this one will be J, and in for the jacket is Qj, and exit is Qj as well. Inlet temperature is Ti, exit temperature is Tj. Okay, Ti and Tj for the jacket is Ti and Tj. So so this one will be Cj, T in is I, then out rho Q Cj Tj. So this one is J, and for the this one is Qj, this one is Qj. It's the same equation, just to change to the properties of the values using the for the jacket. Then minus UA, and this one also must be the J, because the cross-sectional area of the jacket and the cross-sectional area of the tank, they are different things. So if you put the A the same, it indicates the same, then it is wrong. Then here is the temperature difference. So this T, what is the UA delta T? So just like it's not UAT, it's UA delta T, UA delta T. Okay, so the U will be the same one you will put inside AJ delta T. Okay, so what is delta T? So in your thermodynamic, the temperature difference is always follow the exit temperature. Exit temperatures difference of hot and cold. So from here, the exit temperature of the hot fluid is, so this one is the tank. So exit temperature is T. This is the jacketed vessel. Exit temperature is Tj. T is always higher than the coolant exit. Follow your thermodynamic. So it's T minus Tj. So your delta T is T minus Tj. Then you can sub the delta T answer here. To complete the equation. So we have used the thermodynamic fundamentals for modeling as well. So we have learned so much for the first week. It's not honeymoon anymore for Sem 4. You need to really focus. All the modules are very challenging. You have to spend time to do your revision so that you can score well in final for all these 4 modules. So not only week 1, that's why if you still can reconsider, maybe you want to combine some of the easy modules and the challenging modules. But let's say you want to transfer, control is one of the compulsory module. You have to pass, I think, B, right? Depend on the country you want to go lah. So the last question of today is question 6. Okay, question 6. I will share this one with you later once I finish. So question 6.
No, I didn't even pay
A
attention.
blending
Past 10
tank in
minutes.
figure of this mix a processed stream with a liquid
No, fucking redeeming
catalyst.
code in Honkai Story, bro.
Okay.
Wait,
So
I'll send you
stream
later.
1 is pure A. So stream 1 is pure A. And
Yeah.
stream 2 is pure B. But your B, they already mentioned this is a catalyst. A is your target compound. I am sure for any reaction, they don't want the catalyst as your target compound, right? You only use the catalyst so that you can get more A. So your A is your target component. So A. So the composition in the mass balance or in the composition balance is referring to the target compound, which is A, not the catalyst. In this case, I will say my X equals to 0 because none A. Pure catalyst. My X here equals to 1 because of pure A. You do not target on the catalyst, you target on the component A. The blending process outlet mixture then flow directly to the reactor. So this one after that will go into the reactor. The flow rate of stream 1, W1 can vary. So W1 is vary, can change. It is possible to manipulate, adjust the flow rate of W2. So W2, you can adjust. It is because of you have the valve here, so you can adjust. W1 is a constant value. There is no valve to manipulate. So W1 is vary, means every time go in, it will be different value of W1. It is possible to change the W2. W2 is the mass rate. So from here, using a control valve, the outflow, the outflow also can be manipulated because another valve here. So W also can change, manipulate. We call outflow via a control valve in the exit line here. The level in the tank is measured. Unfortunately, there is no way of directly measuring the outlet mixture concentration. There is no sensor to measure the X here. A process control engineer has two options to control the level in the tank. In doing so, she hopes indirectly to minimize the variation in the ratio of catalyst over the A. Means they want to make it like constant, no variation, minimize. So method 1, you can change, manipulate the W2 and W constant. So W2, you can vary or you can manipulate. And then W, keep constant. This is option 1. Option 2 is opposite. You will change the W and keep the W2 constant. So option 1 is, they say W2 you change, then this one W constant. Option 2, this one you change, this one constant. So 2 options. So with these 2 options, I only ask you to derive the equation. So from here, we have mass balance, we have energy balance, we have composition balance. So we have to check whether temperature given. If temperature given, then we will be having energy balance. Like this one, energy balance is not needed because temperature is not given. So we have to summarize here. W1, you can vary. W2, option 1, you can actually, W2, you can manipulate. So I will split into 2. W1 also can vary for option 2, but W2 will keep constant. W manipulate. So this is a summary of the question. W If one manipulate, this one will be constant. So we can use the composition balance dmx over dt equals to, what is the in? The in, there are two streams going in. So you have W1, X1, it is the pure A. Then W2, X2. So I will put here is my 1, here is my 2. Follow the subscript of stream 1 and stream 2. 2 inlets and 1 exit, WX. So you have in minus the out. So WX in minus the WX out. Then you have 2 streams. W1 X1 plus W2 X2 minus WX. So why this one suddenly becomes so big? So you have the dmx over dt. The x here all stand for the A, component A. So x1 is pure A. x2 is non-A. This one is the composition of exit composition of A. And remember, utilize the mass balance as well. Okay, like this one, we don't need the mass balance because we can use composition balance. So from here, how to expand the M? M equals to rho V, rho AH. So this equation will be rho A constant, constant. So DH over DT, rho A constant. So that's why I factorize the rho A outside and then the X. Okay, bracket equals to W1 vary. So here will be 1 because pure A plus W2 non-A 0 minus W and then exit composition. Okay, then we will use bar to indicate steady state. So this is bar, steady state value. So what will be kept constant? What are the things be kept constant? So in this case, W is constant. So I will put bar on the top of W because bar indicate it is constant. So therefore, the final answer should put the bar on top of the W because W is constant to indicate it is constant value. So from here, you'll be having rho A D HX over dt equals to W1 minus omega X for composition balance. And don't forget about your mass balance. dm over dt equals to W1 plus W2 minus W. So rho A dH over dt equals to constant W1 plus W2 minus W. So you have equation 1, equation 2. So this is mass balance. Then you repeat the same for the other side. The other side is W2 is constant. So in this case, I will repeat I will start from dmx over dt equals to in, okay, using everything the same, in minus the out. So you'll be having W1 X1 plus W2 X2 minus WX. Expand the M rho A DHX over dt equals to, now the one constant is W2. So I will just keep this W2 constant. It is easier. You just try 2 times, then you can get the idea already. So finally, you will have rho A DHS over dt equals to W1 X1. So again, this one will give you 0. minus Wx because of none A. So mass balance also the same thing, dm over dt equals to W in minus W out. So W1 plus W2 is the in minus W out, and the constant is W2, rho A dH over dt. Done. So you have equation 3, equation 4. So if you want to solve this one further, you should refer back to the lecture slides, which is your final exam, okay? Maybe your test. Remember this one? Rho A dHs over dt equivalent to rho A dHx over dt plus h dx over dt. Remember this one from the slide? So if you want to solve further, you should actually substitute this equation, which is the rho A dH over dt. So you'll be having rho A x will be outside, dH over dt plus h dx over dt. Rho A is here because you expand. So this whole thing sub the equation 4. It is your lecture slide, but in tutorial I stopped at this point, dHx. So you need to further solve using the one we have learned in lecture chain rule. So that's why in the beginning of the semester, week 1, lecture 1, I already informed you, control is not a simple module. You have to make sure you are energetic for all the classes we have from week 1. There's no honeymoon anymore for any module. You can feel that already. I believe that you already have few classes. So semester 4 onwards, no more honeymoon. Focus, spend 10 hours per module. So around 6 hours for your own revision. So you'll be having 40 hours for all 4 modules. Follow the MI. Okay, so for week 2, we will be having different topics. We will solve using the one Laplace table. Maybe we will be using some knowledge. That's why your homework, please study the Laplace transform topics from your Maths 2. And remember to print out the theorem 1, 2, 3, 4. Last time it is provided, right, in the list of equation. Laplace transform. Yes? No? You have the theorem 1, 2, 3. If no, you go back to the My Times there. I actually share in the My Times for own revision, Laplace transform, something like that. I can't remember whether I print the formula sheet for the theorem 1, 2, 3 or not, but you can always refer to the previous semester. That's all for today. So done.